All right, guys, I think we can go ahead. I've gotten the okay to get started. So thank you for joining me in the last session and the closing day of the closing session of the first day of Build. I'm really excited to be sharing some really cool stuff from the brand new AI for Earth team at Microsoft. And so we're going to talk today about how you can use artificial intelligence to solve some really cool problems. So just in case you're wondering, what exactly did I get in for? What are we going to be talking about here? I just put it all up front, just so you know what you're getting into. So I'm going to start by articulating the AI for Earth vision. This is a fairly new team and a new program at Microsoft, so I just want to make sure everyone is on the same page for what it is. Then we're going to get into some code. I'm going to talk about and announce our first private preview of APIs, and that's around land cover classification. So we're going to talk about what that is, what that means, and what you can do with it, and show a lot of code and some samples. And then all of the code is going to be available on GitHub as well. Then we're going to dive into some more demos and also talk about some other cool stuff that's going to utilize that's going to be worked into the demo as well. Something called Project Premonition, as well as Azure Maps, which are GAing today as well. And then the AI for Earth team was actually, did you guys see the keynote this morning? Who saw the keynote this morning? Yeah, so you saw some of the excitement with Project Brainwave, right? FPGAs on Azure, that's pretty cool, right? So we were fortunate to be one of the first teams to work on Project Brainwave. So we did a large-scale effort on Brainwave. And so I want to tell you a little bit about that, just to get you excited about some of the cool stuff you can do with Brainwave. And then we're going to talk very briefly about the GeoAI data science virtual machine and a new one-click deployment to it to make it even easier to use. A little bit about end-to-end process, and then next steps and stuff that you can just go start coding with right now. That sound good? All right. Okay, so let's start with AI. So it's kind of funny. I did my graduate work in machine learning and artificial intelligence, but that was 15 years ago now. And I like to joke that that piece of paper isn't actually worth very much because the field has changed so much in the last 15 years that it's the problems that were artificial intelligence are essentially solved problems today. In the last 15 years, deep learning has made huge advancements around things like automatic machine translation, speech recognition, face recognition, all kinds of really cool things are solved problems now. And so it really is an exciting time for AI and ML. Like, I feel so fortunate every day that the thing that I love doing, the thing that I'm so passionate about, is having such an explosion right now because it's such an exciting time to be in this field. So and I think we're all aware of the reasons why this is kind of like a heyday for machine learning. Part of it is the fact that the cost of storage has gone way down, right? You can store a couple pennies per gigabyte per month and get a lot of data stored, so you have a lot of data to do your work with. And then with Moore's Law and all, you have access to a lot of computational power. So really, really exciting time for AI. Then if we kind of move over to the other side of the AI for Earth, let's talk about the Earth half of it for a second. I work on a team filled with brilliant people that are thinking about really, really hard problems. Like, there are some really scary problems out there in terms of sustainability. How many people heard about like the death of the last white male rhino? Like, that was a really sad thing. Even if you don't care about the environment at all, just from a machine learning perspective, thinking about the evolution, all the data that needed to happen, like to have all that data lost is a really sad thing. And so there's so many things to think about in terms of sustainability, in terms of how do we get fresh water to where it's needed for all kinds of reasons. How do we increase yield if we're talking about agriculture? How do we work with climate change? How do we deal with a lot of these big things that are happening right now? And so on the team I work on, the AI for Earth team, it's filled with a lot of brilliant people. And these are people that like to sit around and think about how can we tackle these big challenges using technology and machine learning. And so I actually report to my manager is Microsoft's chief environmental scientist. What? Did you guys know we had a chief environmental scientist? Because I didn't until I worked for the guy. But it's really cool that there's a lot of brilliant minds focused on these really hard problems. And so that's really what the AI for Earth mission is. If you guys went to Satya's keynote this morning, you heard him announce AI for Accessibility, right? That grant program. So last December, there was a similar announcement around AI for Earth. And it was made by the Microsoft president, Brad Smith, at an event in Paris. And he announced that Microsoft was publicly committing $50 million over the next 5 years towards projects that would help in terms of agriculture, water, climate change, and biodiversity. And so that's what the program is. So it is a grant program where people are able to, if you're doing machine learning in this space, apply for a grant, and you can get access to some free cloud resources to help kind of solve some of these big problems. And so when we started the program, here's a little bit more about it. There's kind of 4 focus areas here in terms of sustainability. One is agriculture. So in agriculture, there's so many big challenges in the agriculture space. So at a summit, a meeting of the United Nations in 2009, someone made a statement, and it was projected that we actually need to double our rate of food production if we're going to be able to feed everyone by 2050. Just looking at the world's growing population, we're just not producing it in an efficient enough way. And artificial intelligence can help with that, right? Machine learning can predict when's the best time to sow, when is the best time to plant, what are the best crops to put in each places, how can we specifically only fertilize what needs to be fertilized instead of spraying pesticides everywhere, for example. Let's only put pesticides on the areas where there are actually pests, which is cheaper for the farmer, better for the environment, better for all of us eating the food. So there's a lot of really cool things we can do with AI in that space. The next is water. So in the next, I think by 2040, the demand for fresh water is supposed to outpace the supply. And so that's kind of a scary thing when you think about all the things we need water for, not just for drinking, for human consumption, but also for hygiene, for watering plants. There's a lot of reasons that we need fresh water, and getting it to the right place, indeed. That's another great thing that AI can potentially help with. Biodiversity. So biodiversity means all of the, all of the different forms of life, all kind of form are all necessary to maintain our ecosystem. So when you think about things like pollination, decreasing bees supply can lead to less pollination, which is something we need for food. And so there's kind of a lot of very interwoven things that are going on at play. And when you reduce the number of species on Earth, you're losing some of that, the value. And right now, species are going extinct at a rate 1,000 to 10,000 times like where they're supposed to be. So it's a very real problem. And then climate change. And climate change, when you think about kind of even just all the craziness that's happened in the last 2 years with hurricanes and flooding and those kind of things, how can we use perhaps reinforcement learning to make simulations and model and say, okay, if I tweaked this, what would happen? If I tweaked that, what would happen? And be able to make better models of how the world can be. So those are just some of the big problems and some of the ways that AI could potentially help. So if you want more information, feel free to check out our website, and feel free to apply for a grant if you are interested. And as we were talking to people about what, forming the program and figuring out what was needed, we spoke with customers all over the place, and they told us that they needed 3 things. The first was access. So there's a lot of brilliant environmental scientists and stuff out there who have data and have cool problems to solve and have the domain knowledge to solve them, but they need access to cloud compute resources, to machine learning tools, those types of things. And so that's where the AI for Earth grant program comes in. You can apply for a grant, and we can say, okay, here's $10,000, here's whatever amount of money, and then let them be able to actually realize some of that work. The second is education. So again, these brilliant environmental scientists thinking about these hard problems, they can actually take whether they don't have a background in machine learning and kind of just need the basics of machine learning to help them be successful in their domain knowledge is one thing. And then also maybe they have the domain knowledge, but they don't know how to do things on Azure. So we're also providing education and resources and training to help people get up to speed and be successful with these great projects. And then finally, innovation. So we have several lighthouse projects, really big projects where we've invested extra money and we're really trying to make successful. And so I'll talk about, I think, one or two of them in passing today. But we're also excited to announce a set of APIs as well. So kind of finding some things that could be valuable for lots of people, surfacing them up, and then making them available to everyone so that together we can all build a more sustainable future. So these AI for Earth APIs, let me tell you a little more. Hopefully I've piqued your curiosity. So I think of these as like cognitive services for the Earth, right? These are REST APIs. You can call an API and then get back a wealth of information about the Earth, things that could help. And so today we are excited to announce our very first set of APIs, and those are around land cover mapping. And so this is going to be released in private preview, so it's not going to be public on the website, but I'm going to tell you today the process to request access so that you can get access if you'd like to start working with this. All right, so let's talk a little bit more about land cover mapping, which is the first one, the first API. So land cover mapping, the idea is if I have a whole bunch of satellite imagery, I need to be able to make smart decisions with that. And obviously, if you have one little piece of imagery in front of you, you can tell, okay, that looks like a lake, there's water, there's this. But when you want to do that at scale, it's really a computer vision problem, right? If I have a large amount of data, if I'm trying to make decisions for the entire state of Texas, and I need to figure out where the best places to do things, you need to be able to deal with that at scale. So right now, it can be really hard to do. And so land cover maps actually say, okay, given this satellite imagery, I will tell you at a pixel by pixel level, this is water, these are trees, these are greenery and fields, but not non-trees, other green leafy things. These are roads or buildings or other barren surfaces, those kind of information. So this data, land cover data, is actually surprisingly hard to, the process is very manual currently. So one of the most recent ones is still 7 years old. And so our goal here was, okay, how can we make land cover mapping more accessible and easy and available for everyone? And so we worked with some wonderful partners, Azure as well as the Chesapeake Conservancy, and they had done a lot of work manually labeling data in the Chesapeake Bay. And so using that as training data, we built a machine learning model to be able to expose that to a lot of people. So let me talk just briefly about some of the use cases, and then we'll jump into some code. So here's where you could potentially use that. One great thing for land cover use is deforestation. So if you're tracking deforestation over time, you want to know how the amount of trees is going down, this is a great way to do it programmatically and at scale. The other thing where it can be useful is if you're a real estate agency and you're putting up building buildings or something, or you just bought some nice island property and you're putting in a resort, a lot of times there are contractual obligations that you have to maintain, X percentage of trees and such during that building. And so this allows you to do it very easily as well. Then there's a lot of problems around coastal resiliency and monitoring floodwaters and hurricanes and trying to make predictions there. One of our teammates, Patrick, is very involved with, his family is in government in the state of Delaware. And they're actually very concerned. There's an island off the coast of Delaware called the Tangier Island, and they're actually worried about losing their island, like it's kind of eroding away over time. And so really good thing to be able to use these and be able to help and make a difference here. Urban planning, I mentioned that scenario already, very interesting in terms of making sure that you're putting the right things, the right resources in the right place. And then finally, here's one interesting case, is figuring out the best places to plant trees. So this is an interesting story. Right after I had joined the AI for Earth team, I actually met with a city, some city officers in the Office of Civic Innovation for a particular city. And they were telling me that they were really struggling because I guess the temperature inside the city was about 10 degrees hotter than like in the surrounding suburbs. And so I was asking more information about this, and apparently, land covers, trees provide a lot of shade and cooling, and when it's all roads and such, that's reflective surfaces, and they just kind of make it hotter. And so they had a program where they were giving away free trees, essentially, to citizens. And so there are all these free trees available. And then people could basically just come and request a tree and get a tree and plant in their backyard, and very cool. But what would have been really cool, and what they would have wanted to do, and what they told me their desire was, and where it would have been cool to use this, is to do a more data-driven thing. So where can we strategically place those trees to help reduce the overall temperature within the city, as opposed to just kind of making them, planting them willy-nilly as people wanted. So data-driven tree planting is another great thing. And then landslide prediction and root cause analysis. There's all kinds of really interesting things you can do here. All right. So let me tell you briefly, share with you the story of the folks at the Chesapeake Conservancy who really started this work with their manually creating these land cover maps for the Chesapeake Bay.
I've been a waterman on the Chesapeake Bay since 1995. When you're out there on the water every day for that long, you see how things have changed. It's hard knowing there's nothing you can do but watch.
My name is Bob Ingersoll, and I'm a farmer. The demand for our kind of work is only going up, and we're constantly looking at how to expand our yield without stripping the land or polluting the bay.
The Chesapeake Conservancy has been focused on creating tools that help answer some of these questions.
In the infancy of the Chesapeake Bay program, scientists built a scale physical model of the bay to understand how processes worked and to simulate potential solutions. A lot has changed since then, and technology has been the catalyst. The Chesapeake Conservancy has been a pioneer in the field of precision conservation, getting the right practices in the right places, but it hasn't always been easy. Until recently, land cover data was only available at 30 meters resolution and represented what the landscape looked like 7 years ago. Not great for precision planning. We raised the support and spent 18 months working with our partners to create a 1-meter land cover database for the Chesapeake Bay program. This unprecedented project took a lot of effort and massive computing power. Now we are working with Microsoft and using AI and deep learning to accelerate our work, both in the Chesapeake and across the country. Our collaboration is aimed at providing partners with the information they need to make informed decisions. The Microsoft Cloud is freeing up organizations to spend less time on technology and more time on conservation.
Working with a conservancy, I am now able to restore and protect my lands with the same level of precision that I grow my crops. This allows me to focus on what I need to do, provide food for people while sustaining the land and the bay.
I love this water. I love this work. It's a special place out here, and it's up to us to protect it.
All right. So the Chesapeake Conservancy did some really amazing work here. They had put together, mapped over 100,000 square miles of imagery and hand labeled this to be able to create an awesome training set. And so this is over 2 gigabytes worth. It took them over, it took them about 18 months. So a really impressive feat that they did. And so they were using Azure for some of this. And then we started working with them saying, okay, what would be cool is, wouldn't it be cool if we could do this like more on the fly? And so that's when we started building this deep learning methodology to be able to say, okay, given this satellite imagery, let's see if we can classify this and be able to give it back at the 1 meter resolution level altogether. So that way, as it's completed right now, the main problem was since it took 18 months to create that, by the time it was created, it was already out of date. So by building a model, we can be able to jumpstart that process to get it running a lot faster. All right, so here's what we did. So we used the GeoAI Data Science Virtual Machine. I'll talk a little bit more about that at the end. But it's one of our great data science virtual machines. And so taking this labeled training images from the Chesapeake Conservancy, we created a neural net architecture based on the UNet model. It was 23 layers. And then given those test images, we created a land cover map of the Chesapeake Conservancy. And then a little more details on our neural net implementation. It was based on UNet, as I said, 23 layers, a lot of parameters. And we did implement it using the cognitive toolkit, the CNTK. Some of you guys may have used that. It's one of our open source deep learning frameworks. And so we trained that, and I'll talk a little bit more about the inputs and outputs when we get here, just kind of to the next slide. But this is a lot of data. We kind of split it fairly evenly into training and test sets, and we're able to train it fairly quickly. And so the input to this is actually satellite imagery, and it's actually a 4-band imagery. So let me talk a little bit more about that. And then the output is those predictions. So we're going to talk more about that in just 1 second. But let me show you the results first. So here's our input image would be this upper left. Is this a kind of thingy on it too? This maybe? No. So on the upper left-hand side, you see an aerial photo. So this is some satellite imagery that is kind of the input to our algorithm. So that's what you could see from far away. The existing land cover map looks like the upper image on the right. So you can see, since it was created 7 years ago, it's actually a little bit out of date. It's using the old road information before the roundabout was put in. So there's not a traffic circle there yet. And then on the bottom is what our algorithm produced. So on the bottom left-hand side is a land classification model that shows a mixture of probabilities across types. So we have different formats where you can actually get a mixture of the various probabilities, or you can basically like softmax it, and that's what you get on the right, where it gives you the most likely prediction. And you can see, given that image, you can just pass it in and get that right back on the fly and be able to do this very quickly and very easily. All right, so let's talk more about that input data. So we were using data, NAPE data. So this is satellite imagery. NAPE actually stands for the National Agriculture Imagery Program. And this data is it's acquired through the agricultural growing seasons when the leaves are on. So you can see in the pictures kind of the leafy treetops right there. So it is collected at that time. And it's refreshed roughly every 3 years. Every state, based on budget, resubmits it every so often, and but they have to do it at least every 3 years. So you're going to get new data at least every 3 years. And so there's a whole bunch of data out there. It is 1 meter resolution, so you get things down where basically 1 pixel equals 1 meter. So it's that level of clarity. And then it is a 4-band product, is what these images are. So the 3 of those bands are just natural color, RGB, that you're used to. And then there's also a near infrared channel. And that's interesting because that gives you a sense of like the heat, like water is cool and absorbs, thing versus things that reflect are warmer and that sort of thing. So we get that near infrared channel as well, which our algorithm is also using. So if you want to get NAPE imagery, it's actually available in an abundance of places. The link on the bottom is probably going to be the most useful to you. So that is a list of distribution nodes where you can get NAPE data. I included that in there because that was like the best one where you can find a whole bunch of options. So it's all over the place. You can get it through Esri software. You can get it, there's another option, that's what I used, was the one on top, earthexplorer.usgs.gov. And that's nice because you can do the data sets and then you can actually put in the actual latitude, longitude that you care about and type that information in, and then it will give you back the data specific to that lat long. So great stuff there. And then some of my teammates use these other ones as well, so I wanted to throw those up there too. So lots of different places to get the data. So here is the very first look at the API. So as input, you're going to give it some of that satellite imagery 4-band NAPE data. And so you can pass that in as a TIFF. And then in this case, we're calling our classify method. And so some constraints, I wanted to spell these out clearly. So it does have to be a minimum of 256 by 256 pixels that you can pass in. It can be larger than that. Probably max of like 4 megabytes. I wouldn't go much higher than that. And then TIFF, you pass in as a TIFF format. It does have to be 4-band. So what that means is if you have like a drone because we're all about the drones too. We've had a lot of cool drone demos today. A drone that's flying overhead and also getting data is going to usually get it in RGB, because those cameras are just standard natural color cameras. So that's going to give you RGB. It's not going to give you the infrared, the near infrared band that we need as well. So I do recommend you use the NAPE data, because that will give you all of the information. And then it does have to be 1 meter resolution. So that's what what our model is trained on. You can try putting in other stuff, but your results may vary. So 1 meter resolution is what this is meant for. All right, and then as output, what you get is an image. Notice that the image is a slightly smaller size. There's edge effects where we take out a 64 pixel border around that. So I'll talk a little bit more about that in a second. And then you get in the case of the classify method, what you get back is an image where it gives you each of those as a different color. So you can actually see the blue is where the water is, and the light green is herbaceous, which means non-tree plant life. And then the trees are the dark green, and then barren, that brown color where you can kind of see the roads, that is barren. So that can be roads or buildings or things like that. So all of that is spelled out right there for you. And I did want to call out specifically, notice that the input and the output are different sizes. I know as a dev, I would instinctively think I would get the same thing back, so that's why I wanted to call out it explicitly. So it is going to be about the same as the input image, but we are taking out a 64 pixel border around it. So again, if it was 256 by 256 in, you would actually get 128 by 128 classification back. And so let me kind of walk you through that. So let's say that you were interested in getting data on the information in that little peach box that you see right there. So what you would need to provide is actually the blue box, where you give us all the stuff that you want to find the classification to, everything in the peach box, plus that 64 pixel border around it. So give us the blue one. And then on the back end, what we'll actually do is tile for you. So we will feed into the input, we'll break it down into 256 by 256 pixel squares. And so what you'll pass in, or what the input to our model is that solid line that you see there. And then what the model will produce as output is the dashed line. And then we tile that so you can see the first one gives you the first kind of quadrant of the area you care about. The second one will give you the second quadrant, and then repeat that with 3 and 4 to do the same things along the bottom. And then you'll get that back. All right, and then here is some code. So to actually call this, here's an example of some C# code that calls a different method in the API. This one is the details method. And so details gives you something. It'll give you back the image as well, but it also gives you a detailed breakdown of the relative percentages. So let's take a quick look at that. So again, fairly straightforward, calling a REST endpoint. We initialize a new HTTP client. We're adding our subscription key, which you do need, and you can get by in the process I'm going to tell you about in a second in the private preview. We're going to call that endpoint. We're sending in type equals JPEG at the end of that URI. What that means is that I want the data back as a JPEG. You can request it back in several formats. And then that get image as byte array basically converts the image into the stream of zeros and ones that it makes up on disk. And then we're just setting up content types, calling that post async, which will call the URI, get the data back, and then we're parsing this out. So it's giving you JSON back. We're going to parse it out, and what we actually get is something that looks like this. So you can see the breakdown. The details gives you that breakdown, where you see the various types of land cover classification, so barren, herbaceous, the trees and water and such. And then it gives you the relative breakdown. So these values will sum to 1, but it essentially tells you the percentages of how much within the image you have. So I could see, what percentage of trees do I have in this particular area that I care about. All right, so let's actually see some more code, some more demos. I'm going to flip over to my machine, which hopefully hasn't gone to sleep. Oh, it has. Wonderful. All right, and this is a quick look at a website that illustrates this exact thing. So on this particular website, what we can do, I'm going to go here to explore, and we are going to explore a whole bunch of examples. So here are some sample images. And so when I click one of these images, what it's going to do is call our web service and then give you back a side-by-side comparison of the satellite input imagery as well as what you get with this. So let me scroll down here, and let's start with this Roosevelt Island in 2013. and I'll click on that. It calls our web service and then gives you the results back. And in this case, here's the input that you can see, and then the output. And then notice here how how there's a little bit more land that you can see right here, and it's much smaller here. That's because of that 64 pixel border. Remember, that's being taken out, so don't forget about that. You can see that this, the breakdown that we get from the details is the approximate number, percentages of each. So this picture is primarily water, and you can see it does a pretty good job mapping. These are kind of fields, and they're showing up as green. The water is showing up as blue. The buildings along here are all showing up as brown. So fairly good right there. Here's another example. This is North Redmond. So if you go back over the bridge to Redmond, where Microsoft's main campus is, you can see this. And again, we have a fairly decent, it's picking up some water right here, which is good. And then you can see the roads and stuff fairly clearly as well. However, I don't want to give you the sense, so we are, again, this is private preview, so let me set expectations clearly. This is an active project that's being worked on by Microsoft Research as we speak, so we continue to refine the algorithms. So I'll give you an example of where it doesn't work so well here. So take a look at this image, the Roosevelt Island image in 2015. So in this case, the data was taken where there's shadows. There's some pretty high shadows right here. And so if you take a look, you can see big shadows behind each of these buildings. And shadows are cool and dark, and so is water. So that's one thing that's really easy to mistake. And you can see that if we click on this one and give an example, these are all just shadow, but you can see for some of it, it gets it okay because there's a lot more shadow here than you see here, but it does actually get fooled a little bit and does think there's a little bit of water right there when there is not. So that's one of the things that we're actively working on right now to fix. So just to set expectations, it is an active thing. We're really excited to give you an early look at it, but we are still working on this too. Okay, I also want to show you a really cool example of calling this code. So we do have samples available, so some sample code to use this. It's on our AI for Earth GitHub. So if you go to github.com/AI4Earth/samples, there's both a C# sample and a Python sample there right now. I'm going to show you the C# sample. I was pretty close to what I showed you in that in the PowerPoint, so I'm not going to show you that one right now, but go and check it out yourself. But what I am going to show you is the Python one. So here's an example of how to call this from Python within a Jupyter Notebook. And I've done a little bit here to set up the subscription and kind of the URI and stuff. And then here's the two of the methods, classify and details right here. So now I'm going to say, okay, let's set up these URIs here. Just by when we call build classify URI, it's going to call classify. This is going to call details. Just kind of the infrastructure of setting up the auth header and those sort of things to call our service. So I'm going to just shift enter on that. And then here's the actual land cover mapping for Esri NAPE images. I'm going to pass in 2 images here and then do the classification on both of them and generate an output image. So you can see it calling right there. It has a post and responds with 200, so it's good for both of those. And then if I shift, oops, sorry. Not you, no. Right here, go to you. I'm going to actually grab matplotlib and import that, and then we can actually see the results and do some interesting things with the results here. So if I shift enter right here, I'm actually going to build and show you side by side a really cool example of the data. So this is that Roosevelt Island one again, and you can see here's the input and then the output. And then same thing with another image where you can see how it came in and then what it looks like right from within a Jupyter Notebook. And then finally, you can see how to do the same thing with our details. So that will give you those relative breakdowns. I'm just doing a single image here. And then shift enter. Here is a nice layout of the relative percentages here. You can see this is the Roosevelt Island one, so it's primarily water. And then we can also break that down and do some cool subplotting here. So put it all in a bar chart, for example, to see those relative things very easily. So if you want to try these out, this Python notebook is available. The C# samples of calling it from C# is also available. So all of that is on GitHub right now. And I have a link to it at the end. So let me jump back here for 1 second. I do have one more demo. Boom. Okay, so do you guys want one more demo? All right, okay, so here's a cool thing. So I wrote one more demo, but before I tell you about it, I need to kind of set the stage with another AI for Earth project. So has anyone heard of Project Premonition? Okay, only a few people. Oh, you guys are in for a treat! Okay, so Project Premonition is a really cool project that is done by Microsoft Research. And the idea behind Project Premonition is to predict an outbreak of disease before it happens. So let me tell you a little bit about this. Currently, when there's an outbreak of a disease, what happens is a bunch of people get sick, and then they go to their doctors, and then the doctors all report these illnesses to the Center for Disease Control or the World Health Organization or one of these big organizations. That organization kind of aggregates all the data and then realizes, oh no, we have an outbreak, in this area of this disease. But that tends to happen, 2 weeks to a month, after this outbreak has happened. So the idea behind Project Premonition is, can we actually predict that these outbreaks are going to happen sooner than that? And so the way we are doing that is by using mosquitoes. Weird, huh? So mosquitoes, although a very annoying little pest, they land on animals, they land on people, and they draw blood. So they're collecting all of this data about people as they fly around. And so if we capture those mosquitoes, we can actually take the blood that they've drawn and, using our genomics pipeline, actually reverse engineer it to tell exactly what animal it came from and what diseases that animal is carrying. So that's the work behind Project Premonition. And so that's one kind of the cool machine learning part of it, is some of that, the genomics work and that sort of thing. The other thing that's kind of cool is there's actually machine learning in the traps as well. So this is an example of a Project Premonition smart robot trap that will trap the mosquitoes. And you can see it's kind of an interesting looking cylinder. And you can take various lures. We have different lures to lure insects in, and stick them in the middle. So we have some that release like CO2, which mosquitoes are attracted to. There are some that use light. And then you can do various scents and things like that. So you put a lure in the middle. And then there's actually 64 little doors on the side right there. You can see them all open right now. And then we actually have a teeny little machine learning classifier. You guys saw, what was it in the keynote? Scott and not Scott, right? So this does mosquito, not a mosquito, essentially. So it recognizes, based on the wing beats and such of the insects, that's one of the things it uses, it actually will recognize, like a bee or a fly could fly in and check it out and then fly away. But when it recognizes a mosquito, boop, the little trap door actually closes, and we catch a mosquito in there. It doesn't kill them or anything, it just closes the door so that they're trapped in there, and then someone can go collect it and use the mosquitoes. Cool, right? Is that not so cool? Okay, because when I first heard about this, I was like over the moon, and I sat down with the Microsoft researcher, Ethan Jackson, who owns this project, and I'm like, tell me everything. This is amazing. So really, really cool work. So that's, I wanted to show you this just to basically show you the trap, so you could get the visualization of what that looks like in your head. Okay, so a lot of cool work has been done on Project Premonition. It's using the smart traps today. It uses CO2 and white LED light for some of the lures. It's about 90% accuracy on being able to get those mosquitoes and trap just the mosquitoes. And then we've been testing all over the place. There's been some great research done in various areas all over the globe. So a lot of cool stuff there. So taking this story, let's say now, let's do another demo. So let's say that I am, nope, not this one, this one. Let's say that I am a researcher and I want to investigate an area of the globe. Let's say I own disease control in Florida or something, and I'm worried about Zika outbreaks or that sort of thing. So what I could do, or a great use case for land mapping, is if I'm trying to figure out all of Florida, one of the other kind of fun machine learning problems in Project Premonition is, where do you put the mosquito traps where you'll attract the most mosquitoes? And so if you're dealing with like a huge area like the size of Florida, how would you choose that? Land cover mapping might be handy there, right? If you could tell. So mosquitoes are attracted to water. They actually breed in water. I actually got to go see Ethan's lab, and there's little mosquitoes all over, flying. Can you imagine being an intern, like working in the mosquito lab? Like how funny would that be? being trapped in there. They do have panels to keep them closed in, but still, I've got to imagine they must get a lot of mosquito bites. But so working in that area, if I'm trying to figure out where to put those traps, I can take, I could use water as one indicator because they do breed in water. And if anyone has ever tried to take a romantic walk down the beach and then ends up going like this, let's just go back inside, right? That kind of thing, you know that they're attracted to water. And then they're also heavily wooded areas. They tend to congregate in trees, right? If anybody, again, walking through the forest and a lot of mosquitoes. Okay, so basically what we're gonna do here is I have a demo of some code, and what we're gonna do is take one of those imagery, we're gonna run it through our classification algorithm and figure out in this image, oops, not like this, just give me the normal thing. In this image, where are the tree areas, where's the water areas, that sort of thing, and then we'll use that to place a trap in an optimal location. All right, and this is not actually the real logic that the Project Premonition research team is using for placing them. This is a fun demo that I wrote. But you can see the idea of how that could be really challenging, right? And figuring out on a large area where to put them. And this kind of thing where you can do it at scale is a great scenario. So what I'm going to do here is click Analyze Image. Here's my original image here. And I'm going to click Analyze Image. What that's going to do is call our backend web service. It returns the classified image right here, so you can actually see it did a fairly decent job of finding, mapping the roads, and there's a couple points of water right there. And then it also put a red dot on the map, and it said that that is the ideal place. And if I switch over here, the image overlay, you can change from the original one to the classification one. You can see that it actually found, it used, my logic was first look for areas where there are water and woods right nearby. That's going to be the best location. And then if there's no areas like that where water and trees go right next to each other or meet up against each other, then do trees, and then if not, do fields, because you can't actually put the traps in the water, and you can't put the traps in a building or on a road. Wouldn't make sense. All right? So that's kind of the little logic that we wrote. And you can see it did a good job. It actually found right on the edge of that water right here, we have placed our trap. Okay, so this code is on GitHub, but let me show it to you. Oh, and the other thing is this Azure Map Control. So you can see that this is kind of beautifully built into Azure Maps. The Azure Maps team is very excited to announce their general availability here at Build. So they have a whole bunch of really great features that they have built in as well. And so as I look at this map, and as you look at kind of the placement on this map, one other thing that might be useful here is see this little hospitals checkbox. It's actually going to find the hospitals that are nearby too. So if it turns out there is an outbreak, you might want to know, where's the closest hospitals. And that's one of the things that they can actually provide using their point of interest functionality. So as I zoom out like this, I can actually see, and those of you who live locally know that this is probably the Bellevue Hospital right there. As you drive that way, you can see the Bellevue Hospital, and I think there's another one over there too. Yeah, right there, one in Seattle. So I can actually get all of that information as well. So really, really cool functionality. They could also do routing if I wanted to find the best route between setting the trap and getting straight to the hospital or other things. Azure Maps can give you that functionality as well. So very good stuff. And then I did want to call out that code is also on GitHub, and you can find it at on my GitHub, github.com/Jennifer Marsman premonition placement. So feel free to check that out at your leisure as well. And I want to thank Ricky, one of the guys on the Azure Maps team, did an awesome job integrating the map functionality and making the UI a lot prettier. You guys, if any of you guys have seen a Jennifer Marsman UI before, you know that I was not responsible for that UI because my UIs are always so ugly. Very good at algorithms, not very good at UI. So there we go. Okay, so that's another really cool use case for land cover mapping. All right, so now hopefully you're a little jazzed, right? Yes, it would be cool to work with this. How do you get started? Today we are delighted to announce our private preview of these first set of AI for Earth APIs, which are the land cover mapping ones. There are more coming after this. If you are interested in using the land cover mapping APIs, please send email to us, this AI for Earth API at Microsoft.com. And just tell us, you don't have to spend a ton of time on this, but just tell us a little bit about your use case. Which geographic area are you interested in? Like where are you going to be doing the training data? Or where do you want to be able to execute the training? What area on the Earth? What your kind of anticipated load is, how many calls per second. And then if you're willing to work with us, one of the things in private preview is it's nice to get kind of feedback on, hey, this is good, this is not so good, just to help us improve our service. And then after you apply for it, we can generate an API key for you, and you will receive a wonderful series of emails. I think there's like 3 that get generated or something. But one of them, you click on it, and then it takes you to a page. You register, you just create a password, and then it's all managed using Azure's API management on the back end. So you get that, and then you get access to a subscription key, and I will show you that in a second. And then you just take the key, stick it in your app, and boom, you're good to go. And then I already mentioned the caveat. I can say it one more time. I mentioned this during the demo when I showed you a counterexample. But we are actively still in research, still refining this algorithm. It does really well in a lot of areas, and there's some areas where we're still working on it. But it's just to caveat that. But we're really excited to give you an early work, and it's getting better and better every day. So here's what it looks like right now. The AI for Earth API, once you click on that email, the link that you'll get after you send the email, you click on it, it'll take you to a screen that looks like this, and then you have your subscription keys, and then you just go here to show, and it will show your key, take that, copy and paste it in some of the sample code, that kind of thing, and then you'll be able to call our APIs. All right? It will unlock it for you. I also wanted to mention the amazing work our friends on the Azure Maps team have done. They are delighted to announce their general availability here at Build. And so they have a lot of great functionality that is available with Azure Maps. There are maps themselves, and then some really great controls to be able to integrate it right into your web and such. And then the one that I was using was actually integrated into WPF, which was some extra work that Ricky did that turned out incredible. Routing as well, so being able to calculate from A to B using kind of commercial level quality there. The search and geocoding, so that includes the point of interest, which allowed us to find those hospitals in that Project Premonition demo. Traffic, for those of us here in Seattle, we're very passionate about traffic because there's like 2 bridges that connect Seattle to Redmond, and you always want to know which bridge actually has traffic moving on it and not, so we spend a lot of time on traffic. And then time zones as well. So a lot of great stuff here. So why choose Azure Maps? Incredible stuff. As you could see, it's very polished, very beautiful UI as you saw in that demo. And then they are commercial scale routing algorithms, best-in-class traffic data, functionality in over 30 different languages, all on Azure. And the map data is actually powered using TomTom, which is one of the most trusted names in mapping. So very great stuff there. And learn more at azure.com/maps. All right, now I do want to talk very briefly about Project Brainwave. You guys saw some really cool stuff in the keynote this morning, where we talked about Project Brainwave and some of the advances that have happened. So this is a really cool way to do distributed work on FPGA on Azure. And so what Project Brainwave really gives you is real-time AI. All right? So these FPGAs, you're doing real-time inferencing. So you're calling that model, and you are getting a response back in like less than 2 milliseconds. It's very quick response time. And then they're very extremely low cost as well. So FPGAs, if you guys remember, I remember way back in college doing like programming at that level, device level, on field programmable gate arrays, way back in the day, and they are very, you can essentially train them and have them customized, so you're almost skipping a software layer and going direct to the metal. So it does make them very, very fast and easy to deploy. So the ones that we have on Azure have accelerated ResNet 50, so you can train on ResNet 50. And then again, very, very fast and very low cost. And then there's more models coming soon. So how did we use Project Brainwave for land cover mapping, for the work that we were doing? We started with our data. So I kind of told you that we got this data. We had this awesome labeled data from our partners at the Chesapeake Conservancy and Azure as well, their satellite imagery. And so we took this NAEP data, and we actually had 20 terabytes of data, so a huge amount of data to cover the entire United States. So we wanted to see, could we map the entire United States? And that we had this data stored on Azure Premium Storage. And so we built up the algorithms and such. We utilized the GeoAI, data science virtual machine out there, as well as the great Visual Studio tools for AI, which I highly recommend you check out. Because there's some very, very cool stuff in there, making deployment easier and easier. And we used Azure Machine Learning as well as Azure Batch AI to scale higher. And I do recommend that you check out Matt Winkler's talk on Azure Machine Learning, which is happening later on in the next few days. And then finally, we're going to deploy, we deployed these out to FPGA. And this is, again, this ultra-fast inferencing, so you're basically calling it and getting a response. It's funny, we were running it on a cluster of 800 FPGAs, and we actually needed 80 virtual machines just to get it going fast enough to support it, to get data fast enough to keep the FPGAs busy. But very, very cool stuff. And then with that, we can build things like enabling that website to do to be able to provide cluster or land cover information for the entire US. So some of the lessons learned. So if you're a developer and you want to get started with this, like what are some of the key takeaways? I wanted to kind of summarize some of the things that we learned working with some of the early stuff and how it could potentially help you guys. The first point is really not an FPGA specific thing, but just in general. If your data is on the cloud, it's usually easier if you can mount it locally rather than calling through a web service. That's in general going to be faster. So if you can do that, try to do that is my first tip. Secondly, it was just really interesting because the things that we needed to optimize for really changed. Usually when you're coding, it's like the network latency or there's other things that are kind of your bottlenecks. And in this case, those FPGAs were so fast that we just, Project Brainwave is just so fast that we needed to spin up a whole bunch of virtual machines to be able to read data from disk. And we actually had some awesome people on the Azure Storage team helping us like maximize out the being able to read things as fast as we possibly could to be able to send them to the FPGA on Project Brainwave. So we read data from disk and had a whole bunch of, we had to scale out a bunch of machines to be able to read and keep our FPGA clusters busy. And then one thing that I think, for the third point, the thing where FPGA really shines and Project Brainwave really shines is when you do have these batch sizes of one. So we have a partner. One of our AI for Earth partners is this company called iNaturalist. And it's a really cool thing. We actually wrote a blog post about them I think on Earth Day, the week of Earth Day we released it. They're a neat, they have a really cool machine learning problem where they essentially enable anyone to be a citizen scientist. And so you can download their app on your phone, and then as you're outside doing stuff and you see like, oh, here's a really cool bird or an animal, a squirrel or whatever kind of animal, you can actually take a picture of it and then geolocate like where it is, and then you're kind of providing this data of this database of here's all these animals and their various locations and plant life as well. So there's all of this flora and fauna that's mapped, and then it has a little classifier there, so it can actually tell you if it recognizes the species. It can tell you, oh, that's this species. So very, very cool work that they do. And so that's a great example of, you're taking a picture and then boom, that's batch size one. You're just inferencing. You just want to get the data for a single image. And that works extremely well with Project Brainwave. It has a really great, It's really great for those kind of things. GPUs are wonderful when you have a large batch size. You can parallelize and stuff. And and FPGA too, you can just send things through one by one and go really, really fast. But the speed is just amazing. So the key advantages here, just very, very low end-to-end request latency. So extremely, extremely fast, less than 2 milliseconds, as we said, and then very low cost as well. So for more information on Project Brainwave and more fun with FPGA, please go check out our distinguished engineer, Doug Berger, and the amazing Ted Way, who also went to the University of Michigan, go Blue, are giving a great talk tomorrow on FPGA where they will go in depth on some of these things. So I highly recommend you go check that out as well. All right, and then I want to talk briefly about the GeoAI Data Science Virtual Machine. So I've mentioned this a couple times throughout the talk, and so let me kind of take a step back, tell you what it is, and then we are releasing something to make it even easier to get up to speed with it. So in general, how many of you guys have used the data science VMs before, the data science virtual machines? Okay, a few people. All right, let me tell you why I think they're really awesome. On my old team, before I joined the AI for Earth team, on my old team, there was a colleague of mine this summer who wanted to learn more about machine learning. And she had found some sample code on a certain deep learning framework, and she wanted to get started with it. And so she was getting things set up. And I remember it just took her a really long time because there were dependencies, and she had to get everything configured right. And it just took forever. And she was like, this is so hard. Like, why does it have to be so hard? And so I said, that is actually the scenario that the data science virtual machine was born for. Like the data science VM, with the data science VM, it comes with all of these machine learning packages already installed, already set up, dependencies are there, everything is wonderful, and you can run PyTorch, TensorFlow, CNTK, all these things right out of the box and just be up and running and productive immediately. So that is the data science virtual machine. It has this great pre-installed machine learning environment. And the GeoAI data science virtual machine specifically has all the wonderfulness of the data science VM in addition to Esri's ArcGIS Pro software, which is great for visualizing some of this spatial data that you may be working with in the context of AI for Earth. And so one of our great engineers on the AI for Earth engineering team actually created an amazing one-click deploy experience. So you can go to that link right there and click on it, and basically instead of having to go through the Azure portal, and with Azure portal you'll get all the options too, which is great, but it also can be scary and overwhelming. And so this allows you to just basically one-click and take you through a really simple, painless process to get it set up. And it also kind of limits some of your parameter selections. So instead of giving you access to everything, it kind of says these are the ones you're most likely to be successful with and kind of limits it to those choices to make it a little simpler as well. So you can learn more about the GeoAI Data Science Virtual Machine at that link right there, aka.ms/GeoAI-DSVM. And here's what the experience looks like. So if I go and click on that link, it will take me to a site that looks something like this. And you can see the GeoAI Data Science Virtual Machine. Here is, I choose a domain name of my installation, and then the subscription that I want to install it on, and you'll be able to see the subscription ID below. I blurred it out. You choose the location you want to set it up on, and description is optional. And then you click Create. And then it will also ask you for a little bit more information about your virtual machine, so you need to provide credentials. So here is the admin to sign in, your username and password for signing into that Windows virtual machine. And then a unique name. Do keep in mind it does need to be unique across everyone who is using data science or the GeoAI data science virtual machine. So if you reuse names when you're creating these, you can run into issues. So keep that in mind. We have the unique there to hopefully guide you. And then it creates, and this takes roughly 10 to 20 minutes. And I know if my colleague last summer who was trying to get up and running could have had like everything installed and ready for her in 20 minutes, she would have been over the moon with excitement and so happy. So it will create for you, and then you can see provisioning status, and then it will turn to running. The very last step is it will pop up this "we're all done" screen, and it'll show you the status is ready. And then since this is a Windows machine, so a Windows Data Science Virtual Machine, so you can access it via remote desktop. So there's instructions are very simple right there. They give you the DNS name and remind you of your username, and then you can go there. There's also a link to where it exists in the portal. So you can click on the portal there, and it will take you to the right place, and you can modify things in the portal as well. And then it also gives you great information about here's how to clean it up and how to delete it when you're done so that you don't burn credits or burn money there. You can turn it off when you're done. All right, so a couple last things. The end-to-end story. So in general, when we're building these models, you train a model, you evaluate it, you hold back some test data, you test it, you keep evaluating, and then once you're happy with it, you finally containerize it and deploy it. So that's the process that we used. But a colleague of mine, Mary Wall, actually created an amazing tutorial on doing this land cover classification and kind of an end-to-end tutorial to show you how to train your own model to do something like this. So you're welcome to check out. There's a great article that references it that kind of gives you some of the background story, and that's right there. And then there's a tutorial so you can see the whole kind of end-to-end process of training a model, and you can evaluate and tweak it as you like. And then actually using batch AI to be able to scale that work as well. So all of that is available online. All right, so we covered a lot today, right? We talked about land cover, we talked about project premonition, we talked about all of this great stuff. The one thing I do want to take away is that land cover classification is just the beginning. AI for Earth is so much bigger than that. This is the very first API that we're releasing, so we spent a large portion of today's talk on that particular API, but there's a whole lot more coming. We have a lot of exciting ideas, and we're actively building some other models right now. So you can think about things like species recognition, being able to recognize various animals within a shot, identifying individual animals. So not just, this is, a specific animal, but this is animal 5217. If you're tracking animals and monitoring their movement on a large, on a conservatory or something. Being able to predict agricultural yields, estimate floods, do climate simulations. All of these things are possible. So we have a lot of really exciting, really fun work to do. So I wanted to end by giving you all of the great resources. So our AI for Earth APIs, the first set around land cover, do have some good documentation available online. It's great Swagger documentation, ak.ms, AI APIs doc will get you there. The land cover classification tutorial is there as well. You can walk through all of that. I also have a whole bunch of information on the data science virtual machines for GeoAI. So those are great things. The GeoAI data science virtual machine, in addition to having Esri's ArcGIS Pro software, it also contains the land cover mapping tutorial already installed on it. So if you want to work through that tutorial, launching a data science virtual machine is a really easy way to get started with that, because you can just spin it up and go with that. So that's another great thing. And then all the code samples that I showed today are on GitHub. So a C# example and the Python example in the Jupyter Notebook are available at github.com, AI for Earth samples. And then the premonition placement demo is on my GitHub, Jennifer Marsman /premonition placement. All right. So hopefully you're pumped. You're like, let me get started. What can I do right now? A couple of things. If you are doing any kind of work using machine learning in the areas of sustainability, in agriculture, in water, in climate change, in biodiversity, submit a grant. You might, we'd love to help you and enable you to be successful. Go ahead and provision a GeoAI data science virtual machine. We have that nice new, easier wizard to help you get through it, linked again there. And then feel free to request access to the private preview of our land cover mapping APIs by emailing with the following information. And we would be excited to see what you guys do with it. All right. So we've been through a lot today. You saw how there's a lot of big challenges that we have in the sustainability area, but there's a lot of power that we can get with artificial intelligence and machine learning, and that can hopefully help us all make a difference in preserving our planet. So I'm really excited to work together and see if we can all together build a more sustainable future. Thank you.